Okay, so hello everybody. This is Luboš Pekl from CFD Support, and welcome to the webinar on TCFD, the unlimited and focused CFD code. Today's webinar is kind of special because today we can discuss more the details of everything what we do. So for those who are interested more in details, it's the right place and the right time to be and to watch our webinar. So I hope everything works well, and in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. The webinar is being recorded and its recording will be made available on our YouTube channel. And yeah, I think it's time to get to the action. So please let me start with the introduction of the webinar speakers. So this is me. My name is Luboš Pekl. I'm co-founder and CFD support of CFD Support, and my current job at CFD Support is telling the world about us. And today I'm here with my colleague Radek Maca. Hello, Radek.
Hello, Luboš, and hello to everybody who is watching us.
So Radek, are you ready for the webinar?
Yes, Luboš, I'm ready. And I'm looking forward to today's webinar.
Perfect. So I only note that Radek is our head engineer and senior developer here at CFD Support, and he will take care of the technical part of today's webinar. Here is the agenda of today's webinar. So the webinar is going to take about 1 hour, depending on the number of your questions and our answers. There will be 3 parts in the webinar. In the first part, I will give a general introduction to TCFD. I'm gonna point out the main TCFD features and benefits. In the second part, Radek is going to show you a few examples of TCFD, and he will give you a real experience of real work with TCFD. And in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions. Some questions will be answered right in the webinar. The rest will be answered later via email. You can be sure that all the questions will be answered, and especially in today's webinar, you can give detailed questions. There will be time. We will resolve everything really in detail. So take your chance. We are here for you in this. Okay, so about the CFD Support. CFD Support is a private engineering company dealing mainly with computational fluid dynamics. We are located in Prague, Czech Republic. We deliver complete CFD engineering projects. We do various projects on demand all across the CFD field. Then we deliver extensive open form training and consultancy. By the way, in September, we have some seats available on our public open form training, so feel free to apply. We also deliver open form support and custom code development. And of course, our flagship product is TCFD, which is this webinar about. So that brings me to TCFD. So please let me give a brief description of what is TCFD. TCFD is a unique CFD software. It's very progressive because it successfully merged the benefits of open source and of the commercial codes. So the benefits that TCFD inherited from the open source is obviously it's perpetual. TCFD is unlimited for users, jobs, and cores, and it's very customizable. And the benefits of commercial codes are TCFD has professional technical support, it's well tested, it's ready for the industry, it's robust, it's accurate, it's automated, it has its graphical interface, and it has good documentation. TCFD is designed to be a complete CFD workflow that covers all the engineering steps from the pre-processing over the simulation to the very detailed post-processing of the results. It is independent on any other software, and on the other hand, it's fully compatible with other software. So the user simply puts the data in, TCFD does its job, writes the results report, and in the end, the user picks the results. And that's it. So TCFD can be used as a black box and also as fully sophisticated CFD at the same time. So all the options are open, and the beauty of TCFD is that it's the user who decides how deep to dive into CFD or not at all. Please let me stress out now just a quick review of TCFD unique value. So we believe TCFD is unique at least for 4 reasons. And number 1 would be TCFD is unlimited, which means our clients can keep TCFD forever and they can use it for unlimited number of users, jobs, and cores. This gives the investment in TCFD a permanent value, and also this means our clients they can scale their CFD simulations in a really big way. Number 2 would be TCFD is fully automated and focused. So for this reason, using TCFD, the work is extremely effective. Number 3 is we deliver the extraordinary technical support. We keep custom approach to every customer, to every issue. We never leave behind any of our clients. We are very flexible in it, and we support our clients even in matters out of CFD field, for example, in numerical mathematics, physics, IT, or even software engineering. And number 4 would be the real preset tutorials are included. So the new TCFD user has no doubts about how to start or about the best practice settings. There are many other benefits of using TCFD. I'm not going to go for all of them. And maybe I will mention a few important technical details. So TCFD is available both for Linux and Windows operation system. The workflow is very the same, both in Linux and Windows. TCFD can be run in a batch mode on a background, and TCFD can be run, of course, by another software. TCFD can be also used as a library, and it can be also run on clusters and clouds to scale CFD simulations to the fullest. Yeah, the graphical interface is implemented in ParaView, so everything can be done in the graphical interface, from the case setup to the simulation run and the post-processing. Yeah, TCFD can be further scripted in Python. TCFD has a robust automated meshing system, and also the external meshes can be loaded. TCFD is transparent. The trial version is available for free for 1 month period, so anybody can try it, and afterward he or she can decide to go for it or not. The real tutorials are included and are available for all the important machines. So TCFD has many post-processing features. Every single simulation run has its detailed report in web responsive HTML format. TCFD includes visual post-processing called TurboBlade Post. The documentation is available online. And finally, TCFD development is users-driven. Which means we listen to our users very carefully, and if the user miss any feature, we add it to our to-do list, and in the next release we release it in the new software version. We have a few case studies to show TCFD performance. I'm not gonna go for the details. I will just quickly go through. And in case you would be interested in any details, feel free to request the study or more information. So I will start with a fun case study we have. This is example of a benchmark of a simulation of a real existing radial fan for which the measurement data is available. It's a special radial centrifugal fan simulation we did together with our partner ZVVZ Machinery. This particular radial fan is quite difficult to simulate because it has very complicated airflow, including the low pressure ratio together with a high flow rate. This combination is very challenging for any CFD code. We did both steady state and transient simulation of complete fan characteristics, and you can see very good agreement with the measurement. The next case study is kind of similar project we did together with CZ Strakonice. The project was aimed on compressible flow of centrifugal compressor. And again, the measurement data is available, and also we have available the other commercial code results to compare with. Complete centrifugal compressor characteristics were simulated at 3 compressor speeds. As you can see, the results are also in a very good agreement with the measurement data. Yeah. Another study is aimed on parallel scaling. As you know, scalability is one of the most important features of any CFD code. In other words, in modern CFD, it's critical for any CFD code to show a linear speed up with increasing the number of simulation cores, especially for unlimited CFD code like TCFD is. The scalability is crucial. So we made a detailed study on TCFD parallel scaling. The tested case was Francis Hydro turbine. The scaling results are amazing. You can see the key figures. This study clearly proves that TCFD has a very high parallel scaling efficiency. And again, the detailed PDF paper is available for those who are interested in the details. The Spitfire case study. Yes, so TCFD is being extended by the new applications. We continue transforming TCFD to be a great tool also for an external aerodynamics. So recently we made a complex TCFD study of a Spitfire aircraft. We found the original measurement data to compare with the simulation results. The results agreement with measurement were excellent. And again, the detailed PDF study is available. And finally, the last case study we did, it's an optimization study. We did this study together with our German partner company Friendship Systems, who developed their product called Cases. Cases is a flexible CAD platform for fast and comprehensive design studies with simulation tools. Together we made a study on fan optimization. Optimization study is, in general, it's a cycle of many simulations of many designs. The designs are created in Cases and then they are simulated in TCFD. And as a result, the engineer gets an optimized fan model with the higher efficiency. So again, a detailed PDF paper is available for those who are interested in the details. For the future development of TCFD, we have a roadmap. So I can show you just a little of our visions. Our development is customer driven. So our users say what they would like to see, and we do our best to make that happen. As you know, TCFD is CFD based workflow. So currently we are creating TCFD to be a set of plugins. So currently the main plugin is CFD plugin based on OpenFOAM. And for the future, there will be new tools and plugins put together that can work together or not, or they can work also individually. We call this horizontal development. So there will be, for example, finite element analysis, optimization, loop, and anything else. And also we have a vertical development system where the new applications will be added and the high-tech methods will be added. So in the vertical direction, we will always improve and add the new high-tech methods. So that's the roadmap for the future. Now we are, let's say, here, and in the future we will create a network of plugins. And I'm gonna finish with how to get TCFD. So as I mentioned, the trial version is available. Anyone can try TCFD full version for 1 month and decide to take the action or not after that. We have free students program where students can apply with their projects and use TCFD for their project for free. TCFD business model is different from standard commercial codes. The paid version of TCFD is always perpetual, and our clients can keep TCFD forever and use it for unlimited number of users, jobs, and cores. And what is paid for is the first delivery and the later technical support, updates, and maintenance for a certain period of time. We believe TCFD is very affordable. We decided to fight hard for the universities, so we have a special program for universities at outstanding conditions. Private organizations pay a little bit more, but we believe it's still very affordable. And yeah, if you're interested in any details, feel free to contact us, and we will gladly get back to you and tell you everything. Okay, I think now this is it from me, and it's time for the live example where Radek is gonna show you the real experience, the practical experience, how to work with TCFD. Before I pass him the presentation, I will remind you that it's your webinar, so feel free to put your questions to the special window below. We are here for you, and we will gladly discuss with you all the details. So feel free to put your questions. And now it's Radek's turn. So Radek, are you ready for your part of the presentation?
Yeah, hello again. Yes, I am ready.
Okay, so I'm passing you the presentation right now. So here you go.
Okay, thank you, Luboš. Thank you, and hello again to everybody. So what I would like to show you today is mainly concerning the input geometry, concerning the input STL files which are required for the internal meshing tool, which is called SnappyHex Mesh. So I will stay for a while at the input geometry in general, how it should look like, what are the general necessities, let's say, for the input geometry. Then, because we will use the SnappyHex Mesh, so I would like to roughly say what are the principles of this meshing tool. Then we will set up the case, a simple case for such a simple geometry of an axial fan. Then we will do some let's say some modification of the mesh. I will show you how to compare several simulations into one HTML report. Then we will play with some parameters, with layer addition, layer parameters, with some refinement among your object, basically in this case among the blade, and let's say some advanced post-processing tools which you can make manually in the graphical user interface. So this was a short outline of my part. So now I would like to say a few words about the input mesh. So I will take as a help our manual. So the input geometry, what what usually in, let's say, 90% of cases where the access or not access, where the first achievements are not gained, let's say, are in the input geometry. So it is the biggest bottleneck in the CFD in general, how to get the data from your CAD software, which are you using, into the meshing process, and how to get the nice mesh into the CFD code, basically, in this case, into the TCFD. So there are two separate parts, let's say. So first part is the geometry definition. So usually 99.9% of all CFD guys or CAE guys starts in the CAD software. Yeah, it's how to pick, how to design the geometry. Then the next step is the export. So you can, let's say, choose two basic directions. So directly import the CAD geometry into some external meshing software. Which are you familiar with, or which do you like? Or you can export it into different format, usually into STLs, which could be a common input for several meshing programs, and also for the TCFD. So STL generation or external mesh. So today I will mainly talk about the STL's qualities and how to input it into the TCFD. Then all the steps can be done. So if you have good quality of the STLs, then you have very high chance to get outstanding results using TCFD. So what is necessary condition which has to be followed by our geometry? So first one is the general one, which everybody of you knows, is the flow path geometry. So we don't need any solids, we just need the boundaries of the flow path. Yeah, so the boundaries which define the region in which the air or the water or any substance you would like to simulate flows. So first, in case of STLs or the CAD geometry in general, you need to have the geometry of the flow path itself. Then what about the geometry details, which is really hard task. So I like this quote by Albert Einstein, which says that everything should be made as simple as possible, but not simpler. So it means you need to take into account all the details which affect the solution and get rid of all the details which does not affect the solution. Yeah, so it is hard task even to imagine these the details in advance before the simulation. So this is, let's say, basically a stupid example, but I think it is really worth. So as you can imagine, this detail really doesn't affect your solution because there is no flow here. So, and always it brings more complication in the meshing. So to mesh this part is almost impossible, of course. So the basic modification is to really have some simple shapes to help the meshing tool to mesh these or those parts really nicely. So first one is really the simplicity of the geometry. So as simple as possible is really important conditions. Then because we will work with the turbo machinery, and it also in the general in the object perspective, let's say. So every component, every machine can be split into some meaningful parts. So in case of turbo machinery, there are stators and rotors. Yeah, the rotors can be split into impellers or propellers, and the same holds for the stators. We can divide it into the pipes, volutes, some leakages for unshrouded cases, or for pumps, for example, with leakages, diffusers, or general fluid domains. So it is important to split your geometry into meaningful parts. So as an example, we can take this pump geometry. So at the beginning, you have just the geometry of the flow path, defining defining your machine. And then you need to start even in CAD to be possible export it into meaningful components. So we can imagine that this pump can be split into 4 parts. So first one will be the inlet pipe, then the impeller part, then the volute part, and outlet pipe part. So this is the first part of the preparation of the CAD geometry. So in general, and then each component has to follow the following, let's say, conditions or rules. So you should split each component into meaningful parts, which creates then your boundaries in CFD language, let's say, your patches on which you prescribe the correct boundary condition. So for example, for this propeller part, it is meaningful to distinguish and to export separately for example, the hub shroud part, the hub part, at least the part of the blades, but the blades can be split into trailing edge, leading edge, trailing edge, suction side, pressure side, and sometimes also you can export another parts. For example, these. Now I missed the word for that, but never mind. Of course, inlets and outlets and other meaningful parts on which then you can perform separate and special evaluation for forces and other quantities. So the splitting of the boundaries is very important. Then, of course, the interface alignment, the interface meaning the neighboring patches or neighboring parts of the neighboring components. So for example, inlet from inlet to one component should be perfectly aligned to the outlet to the neighboring component, and vice versa, of course, which is depicted here. So it must be aligned really to connect it properly and to work without any numerical, let's say, errors caused by the unalignment of the boundaries. Yes, another example for the volute, for example, TCFD provides also the segment simulation. So the same alignment of the interfaces holds, let's say, if you imagine the whole interface between the, let's say, stator bars and the rotor parts. So the interface which builds the full inlet or outlet must be aligned perfectly to the neighboring component. So for the segment itself, there is not necessary to have some coverage between these two parts, but for the whole inlet, which is building the full wheel, it has to be perfectly aligned. And now we are coming, let's say, to STL property itself. So the most important property is so-called watertight property. So it means that each component should be watertight. So if you fill the water inside there must be no holes to be sure that the meshing process results in really nice mesh without any troubles. What I mean, for example, it is created if you export the STL separately. For example, I think this is the part of the Francis turbine or Kaplan turbine. So if you separate this red part and the yellow part separately, or export or triangulate separately, then you are not sure that there is a so-called point-to-point correspondence. In this case, in which case you will then see the holes at the boundaries of these two parts. But if you export it together, then you should be sure that, or you are sure that there are no holes in the mesh, in the STLs or in the triangulated surface. So this is important parameters which you should keep in mind before you even start generating the mesh. Okay, so let's go for a live example. Let's say So I will start. So here's the webinar. Here somewhere here I have my working directory, and at the beginning we have only the exported geometry of rotor and stator. So I will just show you how the geometry looks like. So this is the rotor part, split it into several parts, let's say two hubs, two shrouds, one periodic boundary, which will be then connected, and the inlet and the outlet. Of course, the full geometry contains also the stator part, but just to speed up the simulation, just because I would like to really show you the results live, so I will simulate today only the rotor part itself. So I will take this rotor STL and set up the whole case. So let's go for it. So I will open the TCFD. So TCFD, or the graphical user interface, was implemented directly in ParaView, which some of you may know, which is a nice tool for, let's say, scientific data visualization. It implicitly contains many features and many utilities and application to how to visualize any type of data, and of course it can be applied to CFD simulation and CFD evaluation as well. So if I open it, then automatically I see the setup for the TCFD. So here in the pipeline browser, we call it TCFD source, which holds all the setup of the simulation, and the item below there is a settings in which I preset all necessary parameters, both for mesh and for the simulation. So first of all, I can save my setup into file to keep it for the next simulation, let's say. So I will go to my, okay, maybe there is a shortcut, maybe here. So webinar working directory. So I will save it as webinar setup, let's say. We can go on. Machine type, it is Axial fun, as I already mentioned. And then we can go and fill step by step all these menus. So what I would like to mention here, there is an advanced button, which enables advanced options of the TCFD. So I will keep it enabled and will comment some of advanced parameters and advanced setups. So inside the simulation, there's time management. So we would like to simulate it in steady state mode, but you can also use the transient. Number of processors, there is no limitation, and my computer, I guess, has 12 cores, I think. So if I go here, yeah, so 12 cores and 24 logic, but I would like to use physical cores, of course. So 12. Solver steady state, this is the advanced option. So for those who would like to develop your own solver, so they they can, and then the name of the self-developed solver can be incorporated into TCFD, but not in this case. We will use the default one. Numerical order, first or second. So because I will start from the scratch, so I will start with the first, and if the simulation will be okay, then I can move to the second, of course. Then convergence check. It is a special check which can terminate the simulation earlier than the preset amount of iteration. For those who are interested in always in manual, you can find all the information. So if I go here, so basically here are the criteria. So if, for example, there are criteria for the efficiency and for the mass flows at the inlet and at the outlet, and if the efficiency differs during the simulation, let's say there is an averaging window which could be, let's say, 100 iteration, and if the instant values differs from the average value less than some prescribed tolerance, then the simulation can be stopped, and all the criteria must be satisfied within one iteration, of course. So both for efficiencies and flow rates at the inlet and at the outlet. Okay, then we can move to the physics. So here you can basically set or check your some predefined fluid names or fluid types, basically just air and water, or custom, in which you can really define the parameters you want for your particular flow. So I will keep it as air. You can keep in mind that some geometry, some simulation can be simulated in incompressible mode, which is always faster and more robust. So, for example, this axial fan has a low speed velocity. It's a low speed fan with a really small compression, so we can, without any doubts, we can simulate it in a incompressible mode, so not compressible. Reference density, reference pressure, because the incompressible solver uses the pressure, so-called kinematic pressure, which is basically the pressure divided by the rho. So therefore you can define the reference pressure usually at the inlet or at the outlet, depending on the inlet or outlet condition, to see at the end the real pascals and not this meter square per second squared, which is the units of kinematic pressure. Okay, so this was the physics, and now we should go for the components where we really define the computational mesh using our STLs. Maybe, as I mentioned at the beginning, you can use any external mesh exported in the Fluent format, so in the MSH format, and it can be directly imported, and then all these steps of defining the computational mesh are disabled because the mesh is ready and defined at the beginning. So today I will be talking just about the STL's geometry and creating the mesh within the TCFD. So directly with STLs, and in my case I have no separate STLs for the given patches, but I have one multi-solid STL. Basically all is defined in one file. So now I have to load it. So I need to go back to my working directory, in which I have preset these STLs, and here's my input geometry. So I will check this rotor.stl file. Now automatically all the parts are loaded into this table, and okay, I need to start filling, of course, all the parameters. So scale factor means the original units. In my case, the original units are meters, so I will keep it in meters. If my original units are millimeters, so I will just check it here that my input units are millimeters, but in my case are meters. The axis is in this case the Z, so I will keep it in Z, but there is no limitation for the axis direction and position. Number of components, if I would like to simulate rotor and stator, so I need to define both, but in this case I will have only the rotor part. Component name, it's up to you. How do you define this component? Everything then is depicted here in this topology graph of your mesh, of your simulation domain. Okay, so number of periodic segments. So as you see, or I can load it again. How it looks like. It is just a segment. So here I need to define how many segments builds the full wheel. So in this case, it's 9 segments. So one segment has, let's say, 40 degrees of this wedge type, of this, let's say, wedge shape. And now I need to prescribe the type of patches and type of boundaries and how, and let's say the refinement level on each boundary. Okay, so first I will start with the types. So rotor blade, there are prescribed or predefined types which has a physical meaning. So it is really simple. So blade, there is a blade type, the same for hub. And now, yeah, the hub and hub inlet. Okay, so hub inlet is this blue part before the blade itself, and the hub name is basically the hub part below the blade itself. So I will define this as a hub because it will generate the hub, or it defines the part which is really rotating. This part is just the wall which is not moving. So this will be hub, and the hub inlet will be just the wall. So the rotor inlet is the inlet, so physical inlet into the domain. Outlet is physical outlet from the domain. Periodic segments, so there are special boundary which is called rotation AMI. Yeah, so it is a boundary condition how to connect two cyclic boundaries which can be mapped one to another. But I need to say that these two are the neighbors, or these two will be connected. So by right click, I will say which is the neighbor of this rotor periodic A boundary. And now we can see if the connection is made, then it is highlighted by different color. And to finish it, shroud is this part, so I will keep it as wall, and shroud inlet is this part, so I will keep it as a wall, and the shroud I will set it as a shroud, which is here. Okay, so I will click on apply, and to be sure I will save my current setup. Okay, the next part is that this part is rotating, of course, because it is rotor. And now I need to define the background mesh size, just to show you the principles of the meshing tools, which is the snappy hex mesh. So I have prepared some visualization. Okay, so I will open new paraview and will load the example. So load state. So anything you made here in the graphical user interface, you can save it and load it anytime afterwards. So just need to find it. Yeah, here, mesh phases. Yeah, this one. Okay, so this is my preset case. So what we need to do is to create first the background mesh. So which only one parameter is basically the cell size of the one separate cell in your mesh, which is defined here. So I will go back for the settings. So a common rule, if you know the wheel diameter in this case is, I think, 28 centimeters. So common, or the magic number for the background mesh at the beginning could be, where is my calculator? Could be 0.28. So diameter wheel divided by the magic number 75. This is our magic number, which is always good choice for the first try. So let's say we define it as 4 millimeters. So my background mesh will have 4 millimeters. And there is a tool how to visualize the background mesh size, or background mesh itself, is by check this checkbox. And maybe because the background is too bright, so I will just make it more dark, yes, to see really the topology of the background mesh. So this is the initial initial mesh for the meshing. And then what we need to preset is how fine will be each part of your geometry compared to this initial background mesh. So which is defined by the refinement levels, we say. So which refinement level says how many times each cells cells which are intersected by your geometry will be refined, how many times. So I will start. So most important part is the blade, of course. So I will set level 1 to blade, so minimum and maximum, both to the same part, and everything else I will set to 0 for the first generation of the mesh. Okay. So this is now my setup, and just to imagine, or just to see how it works, that there are several phases of the mesh generation. So first one is starting from the background mesh size. Then the first phase basically refine all the meshes, all the cells which are intersected, as you can see here, and those cells which lies outside of your geometry are removed. So if I make it visible again, so this is the second part. Then the first phase, let's say. The second phase is that it is snapped to the geometry because of or therefore the name SnappyX mesh. And the last part, if you define the boundary layers, so it is the third phase that to these are the boundary layer is generated. So these 3 steps are made, and now I think these parameters are more clear. So these are the refinement levels, and here the layers. So I will start with the 0 layers, and I think that is all. And yeah, what we need to define is the internal point, just to say the measure which part of the geometry will be basically meshed, so inside or outside. Yeah, so I need to put this point somewhere inside my geometry, so you can really see this cross and the sphere, just to visualize the point. So I need to put it inside, and so I am sure that it is inside. So okay, so this is my mesh setup, and then I will just finish the setup part. Well, the speed lines defines which points I would like to simulate, at which condition. For example, I can define several speed lines, which is useful, for example, for compressors or radial turbines, which really needs to be simulated with different speed lines, but the axial fan operates at one condition, so only one speed line. The rotation speed in this case are 3000 revolution per minute, and minus because it follows the right hand rule where your thumb points along the axis direction, and then your cross fingers shows you the direction of the rotation. So therefore I need to set minus. We can define as many points as we want, but in this case I would like to simulate just one point. Turbulence setup. So as you can see, if I disable this advanced option, then I need to just set the turbulence model and the wall treatment, so standard walls and low Reynolds walls. So I will stay for standard wall treatment, and if I enable it, then you can change the particular parameter of the turbulence model. The inlet conditions. So for this case, I will simulate it with the volumetric flow rate at the inlet. So for this ventilator works or operates at this flow rate, let's say, and turbulent energy intensity. And so this is the inlet turbulent quantities, which can we keep in the default values, and at the outlet we just prescribe the fixed static pressure. 0, it means this is the kinematic pressure, and because we set the reference pressure as atmospheric, so basically we will simulate that behind the rotor there is atmospheric pressure. Okay, initial conditions, so some meaningful condition. So pressure, this is this kinematic pressure, so I will keep it as 0. Velocity, for example, the rough gas could be just pointed into the direction in which the flow flows physically, so it is -1 in this case. And the turbulent quantities, the common, let's say, the common approach is that the turbulent energy divided by dissipation should give something like dynamic viscosity. So I will set it as in this way. It's too much, so in this way. All right, simulation control, some advanced solver parameters like some bounding values and relaxations factors, post-processing, which are important. So averaging window over which the solution is averaged, and in this window the convergence check works. So I will set it to 200 pascals. You can check your favorite units, which will appear at the end of the simulation in the reports. Efficiency probes, so from which part of your geometry you would like to evaluate the results. So what is the inlet? Here it is really simple, but if you have more components, you can check which parts will be used for generating all the quantities and evaluating efficiency and other quantities. So now I realize what I missed, that I need to also denote which part is physically rotating. So in this case, it will be the blade, hub, and shroud. So this is rotating for now, and now I can go back and define the torque patches, of course. So blade, hub, and shroud. All right, and some automatic evaluation, so I will get rid of it for now because we can do it afterwards manually in this case. Okay, and advanced meshing options, so I will make some changes here for the next simulations. Okay, so I hope I didn't miss anything. So I will save my setup and click the check setup, which will check the setup, and now it is saying that everything is okay. So I can go for the simulation. So now I can click here to denote to run the TCFD manager, which is used for the managing the simulation itself. So I will name it as initial geometry. Okay, I will write the case and hold the process by clicking on the run all button. So now the meshing process create the mesh, and now the mesh is created and simulation starts. Okay, now here you can follow the live residual graph, so you can really see the progress of your simulation, and anytime you can visualize your mesh. So if you click here, then I can get rid of the rotor STL, and now if I denote the mesh and check the surface with edges, so I can see my mesh. So it is really rough, but for this webinar purposes, I need to get the results live, let's say. So you can see that now the simulation is finished and the report is automatically generated. So I will let it finish to see then here. So whenever the report is finished, it will appear in this window, which I can enlarge. This one I can rid of, and now you can see the progress of the simulation. So you can follow the report and do anything you want. And now, for example, I can go back and decide that I would like to simulate the blade, of course, with the layers. So I will set, let's say, 3 layers to be applied on the blade. And then I need to go to the snappy part, to the meshing options here menu. And what I would like to do is, for example, I will mention this end cell between levels, which basically adds more cells between different levels, which can be really useful for making the mesh finer just among the parts you want. So I will, for example, set, let's say, the value 5 here. And if I go below enough, there is a add layer options menu. So I will activate the add layers. And now I need to set some parameters. So the expansion ratio is the ratio between the neighboring cell, between the neighboring layer size. Yeah, so the smallest is at the wall and the largest is a part of the wall. The final layer thickness is the size of the layer thickness compared to the cell before the adding layer. So usually I like the number of 0.35, and other parameters are just the defaults, which can be untouched. And I think that is all. So I will approve my changes. I will go back to the TCFD manager, and I will define it as with layers. Let's say my new case is, because now everything is erased. So I will run. Okay. Of course, I need to write the case again and run the simulation again with a different mesh. So I will go back to the residuals. So anytime the simulation starts again, the residuals are restarted, and now I can see residuals for the new simulation. Here in the render view, I can again visualize my mesh. So I can show the mesh. Yeah, so now you can see that I have more cells here, and I have added three layers among the blade. Okay, now the simulation is finished, and the HTML report is generated again. And whenever the HTML report is generated, I can compare these two simulations, for example, together to have one nice report with all information side by side. So I will wait for a moment for the report. Then the report, if I go to my working directory, so I have two simulations here and here, and in the given case, there is a report directory in which the HTML report is stored. And if I open ParaView again, or I will borrow this one, which is already opened. So if you click here to the sources, there is TCFD compare. So new item appear in which you can add as many HTML reports as you want for the comparison. So first of all, I will define the compare. I will define the directory in which the report will be stored, and then I will just say which reports should be compared. So the initial one to HTML, and the second one will be the mesh with the layers. And now here, simply by clicking, the new report is generated, and all will be side by side, as you can see. So now I have two reports compared together, number of cells, Y plus, and other important parameters. And for example, if we compare the efficiencies, so one is here, so 82%, and one is here, 80%. So we really need to do more mesh modification to achieve some converged solution to really have some reasonable mesh for the computation. Okay, so which I did some simulation before, so just to see some simulation with nice meshes, I will go here, which is here, and I have some comparison here. So for example, to compare different boundary layers, so I have here the merge report of 4 simulation with different boundary layer size, and here you can nicely compare how the boundary layer affects your solution. And to see just the difference between these 4 meshes, you can again open each case separately and visualize what you want, for example slices, in which you can nicely see the difference between the generated mesh, so which will be here. Yeah, so I will open, and you can nicely see the comparison of these four meshes. Yeah, so if I zoom it a little bit more, so this has just 3 layers, 5 layers, 7 layers, and 9 layers, and you can make a comparison what you want. So there are basically unlimited option in ParaView how to visualize and compare your meshes, which together with the automatical report gives you really a lot of information to make some nice conclusion with your simulation. So I have some I have more tools or more stuff to show, but my time is up, so I need to finish it at this point and go back to Luboš to conclude the webinar. So thank you, and I am giving the presentation back to Luboš. Okay.
Okay, thank you, Derek. Can you hear me? I guess.
Yes.
I guess you can. Okay, very well. So yeah, let's get back to the presentation, and yeah, we are nearly done. Now it's a Q&A session, your questions and our answers. So I would like to ask you, please ask your questions. It's your time. Just use it. We will gladly answer your questions. So what we have is this. Yeah, what questions we have? Okay, so I'll go one by one. Some will be answered very easily, some will be complicated. So let's see. So Ronald is asking, are the solvers in TCFD CUDA accelerated? I can answer this. No, they are not. We use PC cores and MPI. So no CUDA yet. Do you intend to use CUDA-based solvers? No, not exactly. It's not our strategy to use GPU. So no, not now. So yeah, can we get the recording of this webinar? Yes, everybody receives the recording of the webinar. So don't worry, we will be in touch. Yes. Yeah, Alberto is asking, is it possible to use this software to run parallel on HPC session in my university. Yes, of course. So let's get in touch, and there will be. I'm sure we will find a solution. You can use TCFD on your university. It's this, and do we have another questions? This I have to see. I have to say I can't see any other questions. So I would make a last call now. So please ask your questions. We will gladly answer them. And if not, we would conclude and finish the webinar. So yeah, I have to say I can't see any more questions, and we are also over the time. So I guess okay. I think we should conclude. So yeah. So let's finish the webinar. We would like to thank you for your attention. We would like to tell you that we are here for you. So feel free to contact us anytime in the future. We will gladly support you. It's our job and also a pleasure. So don't worry asking us. We will be in touch. Radek, is there anything you would say?
Yes, I just want to thank all of you. And if you have any question or if you have any particular, I don't know, if you have any particular task to us, or if you would like to see something particular in the next webinar or in some video itself, because we are preparing the video tutorials. Okay, I need to share my screen just to show you. Yeah, so we are preparing web pages with the video tutorials, which will introduce some particular features or particular setup in the TCFD. So if you would like to see something particular or anything, so please contact us. We will prepare the video itself, or we will prepare the focus webinar next time. So if you have any question or any task, do not hesitate to contact us. So thank you, and see you or hear you next time. Bye bye.
Okay, thank you, Radek. And yeah, so we will leave you with that. So thank you for being here with us. And this is it for now. So bye bye.